But like Dr. Marcus said, my name's Kyle Reed, and I work with Dr. Sun at UMKC. And what we do, or what I do for him, is I'm a graduate research assistant, and I help him with climate research using a climate model called the Weather Research and Forecasting Model, or WRF for short. Unfortunately, Dr. Sun couldn't be here. He had a class, so it'll be just me today. And I am a master's student in Environmental and Urban Geosciences at UMKC. And the title of this presentation is The Effect of Urban Land Cover on Local Climate, a look at Kansas City's urban heat island and its mitigation using widespread implementation of cool roofs. Okay, so first off, just about me. I got my bachelor's of science in biology in December from Fort Hays State University. And from there, I went to KU. So I would like to be a doctor or a physical therapist. So I got my doctor of physical therapy degree. And then worked as a physical therapist for about 4.5 years. There we go. Okay, so after about 4.5 years, I decided to return back to school, try a different career. That's when I started back at UMKC in 2017. And then the summer after that, I began as an undergraduate research assistant with Dr. Sun. And that was when I also started with the Missouri EPSCoR project. And then this last May, I got my bachelor's of science in geography. And like I said, I'm a master's of science in the geosciences department at UMKC. All right, so to give you a brief idea of what we do or what we're trying to do, the goal of my research is to provide evidence for the mitigation of urban heat islands through the implementation of cool roofs, which will benefit the local community by improving the city's resilience to climate change. So we all know that climate is changing, but one thing that we are looking into is how we're affecting climate, and especially the local climate in the urban areas, and also how we can mitigate our impacts. So here's an outline of the presentation. First off, we'll start with what is an urban heat island. That is defined as a phenomenon where the air temperature within a city is warmer than that of surrounding rural areas. And that's especially at night. This was first studied by someone from England by the name of Luke Howard in 1818. And what he did was he analyzed the mean temperatures in cities over a 10-year period in London. And he found what he said was the sun in the summer warms the air of the city more than it does the country around it. And some of the ideas he had is why that may be is that the city has more vertical surfaces like buildings that reflect the sunlight down towards the ground. It has the buildings that blocks the airflow through the city. And there's also less moisture in the city, which all these actually still hold true today. And in an article from 2018 by the EPA, they found that in a city of about 1 million people, the mean annual temperature is about 1 to 3 degrees Celsius greater than the surroundings, and that's within the city. And then if you just take a specific one day in particular, the difference can be up to 12 degrees in difference between the rural and urban areas. And then this effect is most intense in the urban core, where you have the greatest amount of infrastructure. So if you take a look in this image I have on the bottom right, this is kind of a general image or a diagram of what you would expect to see if you looked at temperature, ranging from the highest in the downtown areas where you have the greatest infrastructure, and then from there gradually decreasing as you move away from that into the rural areas. So what causes urban heat islands? There's actually multiple causes. One of those is less absorption of moisture by urban surfaces. Anyone that's been in a city has seen something similar to the top picture on the top right. A lot of the rain that falls on the urban surfaces like asphalt and concrete ends up going into the city's water drainage system instead of infiltrating into the soil. And having the less amount of moisture causes a reduction in evaporation, so you don't get that evaporative cooling that you would in more rural areas with less urban land cover. Also, burning of fossil fuels. We all know that fossil fuels emit greenhouse gases, which trap the heat, which help exacerbate the urban heat island. Third would be the tall buildings. This picture on the bottom is an image of Kansas City. And you can see that by having these buildings, the air isn't going to flow through there, and it's not going to circulate the heat, greenhouse gases, things like that. So the temperature is just going to be able to build up within this densely built up area. And then lastly, on the bottom right, you can see the road there. Asphalt in particular has a very low albedo, which is the amount of light that reflects away from the surface. So most of the solar radiation that is coming down to hit the road actually is absorbed by the asphalt, and then subsequently it is emitted as long wave radiation or heat energy. So obviously that's going to exacerbate the heat island also. Okay, so now we'll look into urban growth in the Kansas City metro area. First off, kind of a general view of urban growth in the United States. These two graphs are from data by the United Nations, and that is from this year. And on the top right one, we have the population in the United States of people living in urban areas. And in I believe that was 2015, the census is in the thousands, is 261 million. And they expect by 2050, it's going to be up around 250 million, which is about the population of the United States, if not a little more than it is now. So as more and more people move to the urban area, obviously the urban heat island will expand with it. And on the bottom, we have the percent urban population. So this goes back to 1960, and you can see how it's grown, except for a little bit of a lull in the 1970s. It's continued to increase, and currently in 2015, we were at about 82% urban populated in the United States, which is obviously going to be more than the world's population, which is more around 50%, just over half. So as we go into the future, mitigation of the urban heat island will definitely become more and more important. All right, so specifically now at Kansas City, the region that we're more interested in is the 9-county region around Kansas City that is defined by the Mid-America Regional Council, or MARC, as the MARC region. And this, let's see, there's 4 counties in Kansas and then 5 on the Missouri side. The population in 1980 was almost 1.5 million. In 2017, this last year, it was just surpassed 2 million people. And then they project in 2040 that it could be around 2.5 million people. So like other urban areas in the United States, Kansas City is definitely growing. They project it to grow into the future also. And then interestingly, this bottom part here shows a list of the most intense summer heat islands between 2004 and 2013. And this was put out by the EPA. And they found that Kansas City actually has the 7th worst or most intense summer heat urban island in the United States. And for this, they looked at 60 different cities and compared the weather station data within the urban area to station data outside of the urban area. And the values you see on the right, like for Kansas City, is 4.6 degrees Fahrenheit. That is the average daily urban rural temperature difference over that 10-year period. Okay, so here is a good article by Dr. G, who is actually at UMKC. And they look at classifying land cover in the almost the mark region. There's a couple counties that they didn't include, but this is about the area that we're looking at also. And you can see the red is built up area where you have the city. So Kansas City is focused in around this red area here. And then that is 1972. And as you go to 1979 and 1985, you can see that it expands outward. You start to see the red fill in a little more away from the city. And then after that, it just starts to really fill in from there. And then continuing into the 90s, same thing, it just really becomes more and more dense as you start moving away from the city, especially in 2001, becomes pretty dense. And then this is an image that I had done this last summer, classifying land cover change from 1990 to 2017. And this was using Landsat imagery. Similar color scheme as what they had. The red is essentially the urban area in 1990, and the black is the new urban area in 2017. So again, you can definitely see where it's expanding, especially out here in Johnson County in Overland Park. And then you have some other cities out here in Missouri, more in the suburbs, that are expanding. Since this is already so dense, it's really starting to expand away from that urban core. All right, so next we'll get into mitigation strategies. So first off, there are 5 main categories that the EPA defines as urban mitigation strategies. The first 2 I'll get into a little bit more on the next 2 slides, but those are the green roofs and cool roofs are often studied together, especially in urban heat island and mitigation articles. The cool pavement is a pavement with a high albedo and a greater water absorption. So it's going to help cool the urban area by reflecting the sunlight and absorbing more water, so you have that evaporation to help cool the area. Next is going to be trees and vegetation. So again, you're going to have transpiration from the vegetation to help with the cooling and also provide some shade. And then last, they have a smart growth practice, which seems like to be more of an urban design type of approach to design a city, where they try to speak more for using more mixed land use and things like walkable neighborhoods. So for green roofs, that's basically just where you grow vegetation on a roof. And like I said before, with vegetation, you're going to have more moisture like in the soil. So there's going to be evapotranspiration from the plants to help with that cooling. So some of the advantages is that it provides insulation. It reduces the temperature on the roof, and also since it is vegetation, it's going to absorb carbon dioxide. Some of the disadvantages that they have found is that you have to irrigate it, so you're constantly having to provide moisture, which is going to increase your costs over time. And then they found that with urban heat islands and the green roofs, there's an increase in humidity because you are irrigating it. So if you take into account the heat index, you're also making that you're increasing the heat index. It can be expensive. They've also found because of the cooling, there's decreased vertical mixing, and it's also very heavy. They have found that it is about 25 pounds per square foot when the soil or when the vegetation has been irrigated. So it's pretty heavy in all structures. It's going to be really limited to the structure that can actually tolerate this kind of stress. And this picture on the bottom right is actually, I believe, from Chicago, their city hall. And you can see on the top right why it weighs as much as it does. You've got, I think, 8 or 9 layers here. And then the soil is definitely going to weigh quite a bit. All right, so for cool roofs, this is what we're looking into a bit more. This replaces your conventional roofing materials with lighter colored materials. So it's, as you can see from the picture, your typical roof material, asphalt shingles, is going to absorb about 80% of the sunlight that's hitting it, and only reflects about 20%. So again, after it absorbs that sunlight, it's re-emitted as heat energy or long-wave radiation. And then here with a cool roof, it's a lighter color, so it's going to reflect 80% of the incoming solar radiation. And here on the top right are some examples, some lighter colored shingles, which are kind of a gray color. You've got a flat white roof, which I'm not sure about this, but they can be painted on in applications like this, where it's a flat surface, like a warehouse or something like that. And you also have metal roofs, which will help reflect the sunlight. So advantages of this, it's going to be less costly. There's less upkeep since you don't have to water it, replace the vegetation if it dies, and so on. It doesn't require the additional structural support since you are only since you're only replacing what you already had with something similar to what was there before. Some disadvantages: the albedo will decrease with debris and pollutants settling on it. So that may be one of the only things you'd have to upkeep, is cleaning it some interval of time. There's decreased vertical mixing, again, because of the cooling effect. And some people may consider it aesthetically unappealing since the standard for roofs are the dark asphalt shingles. The lighter roof may be unappealing to them. All right, so next we'll get into prior research of other scientists. So in this field, high-resolution numerical models are commonly used to investigate the urban heat islands and cool roofs. And a good definition of a climate model that I had found by McGuffey and Henderson Sellers is that they are representations of the climate constructed by calculations arising from an equation-based characterization. So the climate model is using equations to help represent different climate and weather phenomenons. And then with our model, the WRF model is a bit more open, so you can adjust and customize different aspects of it. And some of the things that you can adjust include the input climate data, land cover data, and your area of interest or your domain. When you run the simulation, different parameterizations, and the parameterizations are basically weather phenomenon that are subgrid scale. So anything that is less than our resolution, we need basically equations to help resolve that in our simulations. And like I had said, you can change the grid resolution. The actual model code itself with WRF, you can get in and change also if you have enough experience with that, and the list pretty much keeps going after that. Next, so I had mentioned high resolution. This is our area of interest, which is the Kansas City area. This is just kind of a rough idea of what we mean by resolution. Each of these data points is an output from our model. So you can see the lighter black lines are census tracts. So you can see even in these small census tracts within this urban area, you're getting at least 1-2 data points. So it's a good representation for the urban area. Okay, so some specifics more on what we're looking into with the urban heat islands and cool roofs. There were a wide range of model settings, climate data, land cover data, and parameterizations. One thing that's different from ours that we'll get into later compared to a lot of these were that most limit their study time span to only one heat wave, where we're going to look past that into longer time periods. And the focus also tends to be on major metro areas. So one specific one here in 2016 that Dr. Sun was a part of, they investigated the impact of cool roofs in LA, and that was through the end of the century, through 2100. They found a substantial reduction in urban temperatures, and they also found that the effect of cool roofs diminished in their RCP 8.5 simulation, and that we'll touch on a little bit later. But cool roof effect diminished after mid-century, so their thought is that it's better to implement these now than later because you're going to have the best effect currently. And this next study in 2018, this one I picked out because it's, I think, the closest that I could find to where we are in the Midwest. It included Chicago. And they looked at a 7-day heat wave. And that, I think, was in 2016 was the heat wave. And they found a 2.3 degrees Celsius decrease in urban areas using the cool roofs. And they also, interestingly, found a decrease in the fine particulate matters and ozone concentrations, which is interesting because the other study I had mentioned found that there was a decrease in vertical mixing, where you would think there would be a buildup of these particulates if there was decreased vertical mixing. Okay, so now we'll get into what we're doing a little bit more. So like I had mentioned, the model that we are using is the Weather Research and Forecasting Model, which is coupled to an Urban Canopy Model, which is the UCM. WRF is the Mesoscale Numerical Weather Prediction System. It's created in the 1990s by several federal agencies, a collaborative partnership between them. And they recently released version 4 this last summer. And it is, I think I mentioned, coupled to a urban canopy model, which a schematic of that is on the bottom right here. And that is for urban areas because it's going to represent the physical processes that occur in the urban area. For example, it accounts for heat fluxes from different urban surfaces. So the heat, sensible heat flux would be the H on the diagram. So you've got it emitted from the ground, you've got the sensible heat from the roof, and then you have it also at the level of A here. And it also takes into account the temperature at different levels. So again, the roof temperature coming off the walls of the building. And this rectangular prism is supposed to represent a building. So you've got the temperature coming off of that and then also from the ground. And the WRF is commonly used for researching urban heat island effect and cool roofs. So here are the phases of our research. Currently, we're in phase 1, where we're doing more sensitivity simulations. Phase 2, and we'll go into these in more detail. Phase 2 is an early 21st century normal albedo, so just looking at the conditions, and it'll be 2001. Phase 3 will simulate a full summer period in present day. That'll be with a normal albedo in the urban area, and then also a cool roof simulation, which will be a high albedo during that same time period. And then the fourth and last phase will be to look at the urban heat island in Kansas City through the end of the 21st century. And that'll be again with the normal and high albedo cool roof simulations. So phase 1, we have most of these already done, the sensitivity simulations. The time frame was just a heat wave during July of 2012. That was the 17th through the 26th. And just about that time period, the maximum temperature reached 104 degrees Fahrenheit or 40 degrees Celsius. And the average temperature during that entire time frame was about 88 degrees Fahrenheit or 31 degrees Celsius. Again, the area of interest is Kansas City. We used 3 nested domains that we'll look at, I think, on the next slide. And the resolution of the outermost domain was 9 kilometers. And then the next smaller domain was 3 kilometer resolution. And then finally, the domain over Kansas City, the innermost domain, is 1 kilometer. The initial and boundary conditions were provided by the North American Regional Reanalysis, or NAR, data. And land cover, it's kind of complicated, but it was non-urban pixels were from MODIS, land surface product, our land cover product, and the urban pixels were from the National Land Cover Database from 2011. And the reason we used the National Land Cover Database, the urban canopy model that I had discussed, ideally you want 3 types of urban built up area, and that actually has 4 types, but if you combine 2 of them together, you'll get 3, and you can use that for your input. So here are the domains. The one on the left shows the topography of our largest domain, so the colors in the background there. So for this area, we're relatively level, except for when you get out towards more western Kansas and Nebraska. You can see the elevation increase as you go towards the Rockies. And then inside that, you've got your 3-kilometer resolution domain, and then finally the 1-kilometer domain. And then looking at land cover, you can see different types of land cover here. So again, we use 3 different types of land cover, that being the high intensity, medium intensity, and low intensity. And you can, if you look close enough, you can see in this urban core that we had discussed earlier is where you're really going to find the higher intensity urban area. And then from there, it starts to decrease into less intense built up areas. And then you have your natural vegetation and cropland outside of that. Okay, so now here's a comparison of different forcing data. So we've got the NAR that I had talked about on the couple of slides ago, and that is the highest resolution data that we had available, and that is at 32-kilometer grid resolution, and that is only for North America, and it's put out by the National Center for Environmental Protection, or NCEP. Next was FNL data, which is short for Final Operational Global Analysis data. And this was a pretty high or low resolution. It was at 1 degree resolution. So with that, we had to add a 4th domain, which was just outside of the domain on the last slide, and it was 27-kilometer grid resolution. So it added, unfortunately with that, it added quite a bit of time to our simulations. And I think about doubled our simulation time, adding that 4th domain. And then the last one is ERA Interim, which is a European group. They put out this data. And that was also pretty low resolution at 0.8 kilometer. So we had to use the 4th domain on that too. So the scatter plots that you see here, each point is a comparison between the station data, which is on the bottom, the x-axis, and our simulation data, which is on the y-axis. So again, each point is going to be a comparison at each model time output compared to the station data at that same time. So starting out with the NAR data, you can see how it's pretty well centered around this y equals x line. So the closer it is to that line, the better your simulation was. With the FNL data, you can see how there's more of a cool bias. So it's below the line, you're gonna get, our model is showing cooler temperatures than what actually were observed. So unfortunately that didn't work out. And then it's similar to that, slightly better though. The ERA interim also had a bit of a cool bias, and the distribution of the points were also a bit more scattered. So not quite as accurate as what we would have liked there. So here are the parameterizations that I mentioned earlier. So there are many options you can change, anywhere from radiation to boundary layer to cloud processes. So this definitely makes it one of the more difficult aspects, which at times can make you feel very frustrated, but unfortunately that is not recommended. So I needed a good starting point, and that was with a literature review. So with this, basically what other people are doing in their studies. So you can see there's quite a variety in what they are using as far as their parameterizations. So this just gave us a starting point of where to begin with our simulations. And on this next slide, these are the simulation or the parameterizations that I had used. So you have your long wave radiation, short wave radiation. So our main output is the temperature at 2 meters above the ground. So obviously this was going to be one of the main ones, or main 2 parameterizations that we were going to change. and try to see how closely we could get to actual observed values. And then a few of the others we didn't change. The urban surface, we know we wanted to use a single layer urban surface. These next two get a bit more complex, and I think that last one you can use more with energy requirements, like building energy requirements. So with the urban surface being that, the land surface had to be what they call NOAA. So that didn't change also. And then since we're just looking mainly at temperatures right now, the microphysics, which handled the water, the change in phase of different moisture, and the cumulus, which handles the cloud processes, those were kept constant also. So here's a list of the sensitivity simulations that we had run, and they are grouped by the planetary boundary layer and surface layer. So quite a bit of variety. One of the best ones we had was down at the bottom, the MYNN2 and MM5 parameterizations for PBL and surface layer. And then our radiation schemes are RTM and DUDIA. And then you can see the statistics there. And then the statistics we used were the root, mean squared error, mean bias, and mean absolute error. So with these, all three of these, the lower the value, the better the performance. And then it's also commonly found that the combination of measurements is going to be more accepted than using just one to determine the model performance. And all of our simulation data was compared to observation data from the Charles B. Wheeler Downtown Airport. And the reason I picked this is because obviously it's downtown. It's going to give us a pretty good representation of that core urban area with the intense urban heat island. And most of the other airports are centered more around the city on the periphery. So now we've got comparisons of, I just picked out 3 different model setups. And all these use the same radiation schemes, the RRTMG for both long wave and short wave. And then these just vary by PBL and surface layer. So the first one on the left, really the two on the outside, the left and the right, were less accurate. These compare, what we see here are the diurnal temperatures throughout the entire time period from the 17th to the 26th. And you can see it really overestimated the temperatures, especially during the day, and then even during the night with the one on the left. You can see especially on the 21st, it really went below what was observed. And this middle one, the MYNN2 and MM5 PBL and surface layer had the best results, but this wasn't our best simulation. And you can see that this, in general, looks a little bit better than the others. Next is just the anomaly. So it's the difference between the observed and the simulation data. And you can see again how far this one was, the one on the left was off. So it's about 6 degrees under that one day, and then almost up to 6 degrees over on multiple days. And then the one on the right, quite a bit of a warm bias. It's overshooting the maximum temperatures pretty regularly. And the middle one, still a little warm, but more of a distribution on the bottom, undershooting also. And undershooting some can be okay, which will help, I guess, cancel each other out. So it's not a huge issue if it's a little bit both ways, but when you get pretty extreme, it becomes more of an issue. And then finally here we have the scatter plots like we did on the other one. And this one on the right, you can see how they're all pretty much above that y equals x line. So it's going to be a warmer simulation. The one in the middle, pretty well distributed, pretty well centered around that line. And then the first one also not too bad compared to the others. And so this is a look at the simulation data here. On the right, we have just one output time. And all this is the temperature at 2 meters. So on the left, again, is the land cover. You can see the downtown Kansas City area. So if you compare the two, you can see how the spatial distribution of the land cover and urban area pretty well represents the increased temperatures here. And again, I picked a 1 a.m. time because that difference is going to be greater at night than it is during the day. At night, you have the heat retained by the urban area, where over here in the rural area, it's getting rid of that heat that built up during the day. Okay, so also another type of sensitivity simulations that we had done were to change the urban albedo, or the amount of light being reflected. The normal albedo study or simulation that we did was 0.2. So it's only reflecting at 20% of the light coming, or sunlight, solar radiation coming onto it. And we also had a medium albedo of 0.5 simulation and a simulation of 0.8, which we called our high albedo simulation. And all of the simulations were set up exactly the same, same domains, land cover, parameterizations, forcing data. That way we could compare them easily. And then the only thing that was different was, again, the albedo. So on this chart, again, shows, like the last one, the diurnal temperatures. The normal albedo is in the green, and it is absorbing the most sunlight, so it's going to have the warmest temperatures throughout the entire time period. And then in the red, you've got the medium albedo, and then blue is the high albedo. So pretty much what you would expect for the most part. The more light that's being reflected, the cooler it's going to be. You do have one area in here where it doesn't quite follow that, but that may just be from model noise. So if we just averaged it out over multiple station points, it may kind of smooth that out to where you have the same representation as you do with the others. And next we have the differences between the simulations. So we're just subtracting one simulation temperature from the other. The first one we have here in the blue is the high albedo minus the normal, and it gave us our greatest impact using the cool roofs. And you can see, I think on average, if you average the entire time, it's about 3 degrees less than the observed values. The medium minus the normal is that top red line, and that was about 1 degree difference between the two. So you're getting an extra degree of cooling by using the high albedo as compared to medium albedo. And then finally the high minus the medium, I guess that was the 2 degrees difference between those two. And the medium minus normal was the red line. Okay, and then next, so what you can see here is different times of output for the entire simulation, or average for the entire simulation. So our simulation puts out output every 3 hours, which was 7 p.m., 10 p.m., and so on. And you can see this is the difference between the high albedo and the normal simulation. The cooling within the urban area is the greatest at 4 p.m. and 7 p.m. So you get your greatest effect in the later afternoons. And this can speak to what they call cooling efficiency of cool roofs. So basically just looking at when are they most effective. During the daytime, are they more effective later in the day? So that's one thing that we looked at a little bit also. This next slide is kind of the why behind what we do. On the right, you have a map this was from the MARC, or Mid-America Regional Council. And this just shows the poverty in Kansas City and where it's located. And if you remember our other domains, or there we go, our domain here, the core urban area is where you have the highest amount of poverty and the highest amount of built up area. So that in theory is going to have the greatest temperature increase. You're looking at the urban heat island as compared to more residential areas in the city. Next, I use my art skills to kind of represent this area on the right over here. So again, you can see where it's the areas with the greatest poverty fall within the areas of the city with the greater urban built up intensity. And then also the higher temperatures that we had looked at before also fall within this same area. And here's what we can do if you, again, employ a widespread implementation of cool roofs, the amount of impact we're able to have on those temperatures in the urban area with implementation of that. So that would definitely improve things like quality of life and other things like that for people in these areas that may not have the means to help combat or adapt to these increased temperatures. So we all know, so why does this matter? We know that the Midwest heat can be pretty miserable at times. So again, it's going to improve quality of life for everyone in the city. Individuals with lower income are less likely to have a car, so they're going to be outdoors walking to the store, to work, to get to the bus stop. So that's going to be important for their daily life in that aspect. And also, there are studies that link higher crime rates with greater temperatures. I know there's different ways to interpret the data, but there is some thinking along those lines that higher temperatures can affect crime rates. Okay, so our next phases that we're going to be looking at here in a bit are phase 2 and 3, which phase 2 was the early 21st century simulation, and phase 3 was the present day simulation. So the second phase is going to be the entire summer in 2001, and then phase 3 will be the entire summer during this last summer in 2018. We'll use the same 3 domains. Initial and boundary conditions will be the NAR data set. Land cover will be represented by NLCD 2001, which is the land cover data set they put out that year, or for that year. And then the present day simulation will have the NLCD 2016, which last time I checked was due out December 28th of this year. So we get to take a look at that. And the present day one, like we had mentioned before, will include a cool roof scenario also. And these simulations will be compared to assess the change in the Kansas City's urban heat island during the present day and early 21st century. Okay, so next will be our last phase, which will be the largest phase of them all. And this is looking through the end of the 21st century. So the simulations will again include the normal urban albedo of 0.2, and the second one will have the deployment of cool roofs, which will be at 0.8 albedo. Again, the time frame will be into the 21st century, same domains. So with NAR data, we're unable to use that into the future. So we'll have to pick a global climate model to use for our input data for the weather and climate conditions. And we'll likely use the RCP 8.5. So for those that may not be as familiar with the RCP, these are representative carbon pathways. So they're different scenarios that estimate future greenhouse gas emissions. And you can see on the right, there's 4 main ones here. You have the RCP 2.6, which basically you're halting a large amount of your greenhouse gas emissions immediately, and your radiative forcing is going to decrease through the end of the century. Then you have 2 middle of the road scenarios, and then the one we'll be looking at is the pretty much what they call business as usual. So just we continue to use coal and fossil fuels the way we do now, and so our radiative forcing is going to be increased pretty much linearly through the end of the century. And the land cover will have to come from a different data set, so since it's in the future. And what we'll use is the Integrated Climate and Land Use Scenarios, or the ICLUS. And this is put out by the EPA, and it projects change in impervious surface through 2100. And this also has different scenarios based on the amount of urbanization. So we'll have to decide which scenario we'd like to use there for our land surface or land cover. And then the last aspect that we would also like to do or undertake is using our results to apply them to biometeorological indices. So this biometeorology is a field defined as science studying interactions between atmospheric processes and living organisms, which can include plants, animals, and for us humans. So we can use our information that we get from the model and input it in these calculations and these indices to obtain basically what we're talking about here with the heat index and the UTCI are apparent temperatures, or how it feels to humans in that area, in that environment. The heat index everyone's probably heard of, and it takes into account temperature and humidity. The Universal Thermal Climate Index, or UTCI, is a bit more advanced. It's recently been developed, and that was in 2009, and this took place in Europe between the International Society of Biometeorology and the European Cooperation in Science and Technical Development. And that input, or I guess input for those that we'll get from our simulations, include the mean radiant temperature, air temperature, vapor pressure, and wind speed at 10 meters. And the scale for that is on the right. So basically you get a output from this index that you can compare to these different categories here, which ranges from extreme cold stress to extreme heat stress. So one advantage you can see here is you can use it during cooler periods, which with the heat index is really meant for just summer, and its categories are based on your likelihood of getting heat illness or heat-related illness. Another advantage to the UTCI over heat index is that it accounts for wind speed, which obviously is going to cool you down on those hot summer days. And with the heat index, there's also different equations based on your humidity and temperature. So it can be, they're both complex, but that's just one complexity of the heat index. And next we'll get into our summary. So with WRF, it was shown to reasonably simulate the diurnal 2-meter air temperatures during the July 2012 heat wave. And again, there's a scatter plot on the top there. WRF would simulate the urban heat island in Kansas City well, and that is the middle one you see there, how we could see the distribution of the land cover being urban compared to where the temperatures were greatest. And the mitigation effect was greatest in the afternoon, late afternoon, 4 p.m. and 7 p.m., which were during the hottest parts of the day. The cool roofs with the highest albedo had the greatest impact on the Kansas City urban heat island. And again, the average was about 3 degrees Celsius lower than the normal albedo. And our next steps will be to look at the urban heat island from 2001 and then also the present day in Kansas City. And then we're going to extend that through the 21st century using both the cool roofs and normal albedo there also. And then also investigating the effect using the apparent temperature indices that we had just mentioned. And with that, I think that is it. Just some acknowledgements there. Does anybody have any questions? I'll go back up to this slide.
Questions for Kyle?
Was it that good?
Well, you know, I have one, and I know it was probably done in the interest of time, but yeah. You talked at length about the different parameterizations that you're employing within the WRF. Does your urban canopy model have the same kind of flexibility, or is it fairly rigid? I'm not familiar with those.
I'm sure it could be adjusted if you know enough about the code, but for us, it's fairly rigid using the 3 domains, and then from there, there's not much customizing it from that aspect.
Okay, so it's, I mean, I think the WRF was kind of always, from the beginning, was designed to be fairly modular.
Yeah.
And it sounds as though the canopy model that you're using is, if you really want to get your hands dirty, maybe. I mean, I'm not familiar with this one at all, so
I think that's right. If you want to get your hands dirty and get in with the code, you can alter pretty much anything in WARF.
Okay.
So that's one of the good things if you know enough in that realm to do.
Okay. All right. Thank you. Anybody else?
Hi, it's Tim. Can you hear me?
Yes.
So, quick question on the urban heat island. You talked about moisture in the beginning. You mentioned that urban areas have less moisture. Do you mean that in an absolute sense, or just low humidity because of the higher temperatures?
I would say in the absolute sense, because it's running off into the waterways or into the city's water drainage. As far as the temperature or the humidity, like absolute or relative humidity, check. But you're definitely getting the water runoff through the system because it's not absorbing into like it would soil in the rural areas.
Yeah, do you have like observations like the cities versus other areas as far as the amount of moisture? Because I would think if you increase the temperatures that much in a city, the amount of moisture the air can hold will go up exponentially. So I think the humidity would be lower, but I'm not sure of the absolute moisture. Or does the literature actually show that? Just out of curiosity.
That's a good question. I would have to check with that, but I'm not 100% sure. We've been looking more at the temperature as far as the effects of moisture.
Yeah.
You don't see it addressed much when you talk about when these articles look at the urban heat island and cool roofs, unfortunately.
No, I think my contention, just being a weather geek and I looked at weather stations and dew points and temperatures like over all kinds of areas. My guess, what I take would be that your dew point depression would be higher because you have a higher temperature, maybe the same dew point. I'm not sure if the amount of moisture in the air would be absolutely lower.
Yeah.
But I think that your humidity would drop because of the higher temperature. Your dew point depression would be higher because of the higher temperature as well.
Yeah.
That's just a guess, though.
Yeah. No, that makes sense. I would say that definitely makes sense to me too.
And I guess a follow-up, I think this is really interesting work. I worked a lot with outreach and gardening, and I think the other way to mitigate the urban heat island, this idea of cool roofs, I think is a terrific idea. I know St. Louis does it. Also, incorporating kids into this.
Oh yeah. Yeah, definitely like the urban gardens and things like that.
Exactly.
You could use those in cities. So yeah, that would be a good idea for the green roof type of application.
Yeah, feel free to talk to you offline about that because I've already done a project with this and I'm looking at data as we speak. So,
okay.
You're welcome.
Okay, sounds good. Thank you.
Okay, thank you.
Anyone else? All right. Thank you, Kyle.
Thank you.
If I could, again, I would appeal to everyone, if need your updates. So thanks, and everybody have a good day.
Thanks.
You too.